how can we verify if devices are truly addressed correctly? How can we do that? You know, if we think about PC1 right now, let's say it has the IP address of 10.1.1.10/26. And the default gateway has an IP address of 10.1.1.1/26. Are they truly in the same subnet? Are they truly in the same subnet? Well, we have what? The same subnet mask. But that doesn't mean anything, as we'll see here shortly. Because just because they have the same subnet mask doesn't mean they are in the same subnet. Because that subnet mask identifies the network portion of an address. Do you recall learning that way back in maybe your CCNA routing and switching studies? Yeah, the subnet mask determines the network portion, and it's this network portion that has to match between two devices in order for them to be considered in the same subnet. So let's examine how we can determine this. Let's take the address 10.1.1.1 and let's convert it to binary. That's right, I said binary. Don't panic, don't panic. Not yet. I'll show you a shortcut in a couple of minutes. And let's take the address also for 10.1.1.10 and let's line them up. Let's line them up perfectly. Let's also grab the subnet mask. And when we grab the subnet mask, let's make sure we line up the bits of the subnet mask perfectly as well, right there. All right, so everything's looking good. We said the subnet mask defines the network portion. So what is the network portion for 10.1.1.1? It is going to be all the ones in the subnet mask. So the ones in the subnet mask end right there. Meaning that the network portion for 10.1.1, that address there, is going to be those first 26 bits of the IP address. Since 10.1.1.10 is also in the /26 or has a /26 subnet mask, we can now look at the first 26 bits of that IP address as well. If the first 26 bits of 10.1.1's address and 10.1.1.10's address are the exact same as they are here, it means they're in the same subnet. And that's how our devices determine whether they need to send the traffic locally or whether they need to send it to their default gateway so it can be routed onto another subnet, simply by looking at these network bits. Now let's say, in our topology, PC2 had the IP address of 10.1.1.65/26. Is that in the same subnet as PC1 and the default gateway? Now notice PC2 is in VLAN 10, which means it has to have an IP address within that VLAN 10 subnet. So if it doesn't, communication with PC1 won't occur. Communication with the default gateway won't occur. But how can we figure it out? We simply take that address that we have, so it would be 10.1.1.65. It would also be a /26 address, as we said in our example. So let's add that in here. So since it has the same subnet mask, I'll just line it up right underneath. Just like that. Now I want you to pay close attention here to the network portion of this address. If we follow along the ones, doop, right there, look at that. The ones end right there in the subnet mask. Is that the same bits between our green address and our purple addresses? No, it's not. Those address bits are different. We can see right here, everything's the same up until this point. This is a 1, whereas this is a 0. So therefore, completely different subnet, which means we will not have communication between the devices, or PC1 and PC2 as an example in VLAN 10, and that default gateway. Why? Because of this right here. PC2 is addressed incorrectly. And we were successfully able to determine it. But let's take this a little further. I want to show you a shortcut to do this. So you're very, very quick if you are in a troubleshooting scenario and you need to identify whether two devices are in the same subnet or not. So for example, we have a /26 subnet mask, meaning we have 26 ones in that subnet mask. And if we examine the ones, we can see that the very first octet is full. The second octet's full. The third octet's full. And then the fourth octet only has 2 values in it. So we only care about the very last octet, that fourth octet right now. And we want to look for the very last one. And what is the very last one? It's the one we see right there in the subnet mask. And what is the decimal equivalent of that bit position? Well, when we're dealing with binary, we have values such as 128, 64, 32, 16, 8, 4, 2, 1. So let's figure this out here. We have 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. The decimal equivalent of that bit position is 64. Why do we care about that? Because this 64 means that we are counting by 64 in the fourth octet. It's defining our block size, our subnet IDs. So in our case, we have the 10.1.1.0/26 network. And then the very next subnet would be 10.1.1.64/26. And the next one would be 10.1.1.128, exactly, /26. So that's all we're doing is we're counting by 64 in this fourth octet based on the fact that the subnet mask is a /26 and that very last one falls within the fourth octet. So now when we just look at the IP addresses, we can line them up. What do I mean by line them up? Well, this address right here belongs in the first subnet. Why? Because 10.1.1.1 falls between 10.1.1.0 and 10.1.1.64, the very next one. Same thing is true about 10.1.1.10. It falls within that subnet. So we can confirm that both those addresses are in the same subnet. But if we examine our 10.1.1.65 address, it falls within that subnet right there. It falls between 10.1.1.64 and 10.1.1.128. So therefore, without even having to do binary, all we did was write down this value, this value, this value, this value, this value. We were able to successfully determine that 10.1.1.65, which we said in our example, was PC2's address, is incorrect. Because PC2 needs an address within the 10.1.1.0/26 subnet, when right now it has an address in the 10.1.1.64/26 subnet. So this is an important ability to have. It's an ability we learn in CCNA routing and switching, but a lot of us did that a long time ago. So hopefully that was a great refresher for you, and hopefully it'll come in handy in your future.